moving from kinematics, we're going to look at forces. In other words, we want to say what causes motion. We've described motion with kinematics. So we're going to look at what causes the motion. And our cause of motion is a force. And so a force is a vector. It's also a vector, which means it has a magnitude and a direction. So we're going to draw our force. Looks like this. And we're going to really start with Newton's second law, which is force is equal to mass times acceleration. Strictly speaking, it's adding up. This sigma means the sum. Let's add up all the forces. And altogether, the forces tell us what acceleration we have. So the first thing we notice about forces is the units of a force units, and I use a bracket to tell me about units. The units of force are newtons, okay, which is also mass times acceleration, which would mean that it would be kilograms times meters per second squared. So that takes us back to our fundamental units of kilogram, meters, and seconds for our MKS system, if you like. So what we can do is start to look at objects and look at what happens when we apply forces. So if I have this object like this, and there's a force in this direction, and a force in this direction, and let's say a bigger force in this direction, and a bigger force in this direction, we start to read these force diagrams. These arrows tell us about the forces. And the first thing, if I've drawn these to scale, is if we say all of the up and down forces are equal and the left and right forces are equal, then we can say that, in fact, all of the forces balance out. If I add up all these forces, force 1, 2, 3, and 4, all of these forces, force 1 plus force 2 plus force 3 plus force 4, you can see that they cancel out, so this gives me a 0. So the sum of the forces is equal to 0. I've added them up, the net forces, or if you prefer, total, either way, that equals 0, which means my acceleration is equal to 0. Now here's where it gets tricky. Just because the acceleration is 0 does not mean that it's not moving. This can certainly be something that's at rest, but it could also be, so it could be that v is equal to 0 and it's just sitting there, or it could be v is constant. And in fact, this can be a diagram of a car moving at a constant speed, going 55 miles an hour north, where the engine maybe is pushing the tires against the road, so it goes in this direction, and this one arrow is now the air resistance, so these are balanced out, this engine and air resistance, and then this is the pull of the earth down, and this is the force supporting it, and so you have a car that's going 55 miles an hour, and all the forces that act on it give you 0. Now you're probably going, yes, but I have to push the gas pedal. And that's true, because what we pay for, if this is our forward direction, so this is, suppose this is going forward, okay? And this doesn't have to be bigger. These can be the same. We're going 55 miles an hour, for example, this direction. So we'll say for this object, this car, we're going 55 miles per hour, and that's forward. What we're paying for is burning the gas to run the engine to make these wheels, which are really very small for this object, to go forward. We really don't care in terms of what we pay for. I mean, we do care about the air resistance. In fact, we want to reduce this so we don't have to provide so much force to go forward, and that's why we tend to round off these to make our cars more aerodynamic. And this is only minimally more aerodynamic, right? And of course, you know what cars look like to get more and more aerodynamic. Okay, the point here is that, and we can sort of see Newton's first law in this, is that if an object is in motion, it wants to stay in motion. That's Newton's first law, unless it's acted on by a force. And what that really means is an unbalanced force. If suddenly we were driving this car somewhere where there was no air resistance, so we didn't have this, then we wouldn't need this. It would just go and continue to go, okay? And so if an object is moving, the best way to think about this, the cases where we have very little resistance to motion are like on ice surfaces or on an air hockey table. You know, things can bounce around for a really long time because this force resisting the motion, air resistance and friction, tends to be very, very small. It does take a force to get things going, but once we get up to speed, then these can be balanced. So if we wanted to look at the car, okay, so here's our silly car, but here we go. Ooh, this became a different car all of a sudden. There's our car. And if I have a force diagram that looks like this, what that tells me is the acceleration is in this direction. So this is a bigger force than this, so this could be a car starting off and going in that direction, okay? So that could be a car starting off. If you're braking, then it might be that your acceleration is actually in the opposite direction. And so you have this force suddenly become smaller than this air resistance force. In fact, it often goes in the same direction, right? When you put on the brakes, you have a force, you have two forces that point in that direction to slow it down. So these are just descriptions of how we start to understand these diagrams. I do want to point out that these diagrams tell you nothing about where an object is going. So here's a box of some sort, and let's say we've got a force 1, and force 2. Now, this is clearly accelerating, right? Force 1 is in this direction. Force 2 is in this direction. So altogether, the forces add up to be like this. This is my force total. So that's the direction of the acceleration. But the box could be moving in any direction. It could actually be going this direction with a force like this, which would tell you that it's being slowed down. Or it could be a box that's going like this, and so in this direction it's keeping its same speed, but then it's got this force that's providing an acceleration. Well, it does have some upward component, so it would be accelerating it up and to the right, so it would start to move in that direction. Okay, so the direction of the force or the direction of the acceleration shows you nothing about the direction that an object is moving. Think back to circular motion. The acceleration is toward the center. Do you move towards the center? No, you move going around a circle. Same thing for forces. So don't let forces, that we're going to draw a lot of force diagrams, we're going to use them to get at our acceleration. But what direction something goes is determined by the velocity vector.